recording. Okay, it's being recorded, so you may start.
All right. So, okay, here. So, can you see the screen?
Yeah, perfect.
All right. Okay. It's kind of strange talking to the screen, but you know, nowadays you have to get used to that.
Yeah, just a comment. There is a banner there. If you click on the right side, it will disappear. There. Okay.
Ah, you mean this one? All right.
Yeah. Okay.
All right. Yeah. So let me start then. So I have about 50 minutes, right? You mentioned correct?
Yeah.
Yeah. So that's what I would suggest. If someone has a question, they can interrupt me anytime, or you can interrupt me anytime, or also at the end of the talk. So it's totally up to you. Feel free to interrupt me when you want. So yeah, today I'm gonna show some of the results that we have obtained at the Paul-Drude-Institut, PDI, so in Berlin, and about epitaxial growth of van der Waals heterostructures. So these are the collaborators or co-authors of the results that I'm going to show here today. So there's, of course, a lot of folks from PDI that are involved in the research that I'm going to show you today, and also colleagues from other institutes in Berlin and in Germany. And also some of the work shown here today was also done in collaboration with colleagues from Spain. And yeah, so of course, you can never work alone. You should never work alone, but you should always join expertise and efforts to get the best you can out of the research you're doing. So I'm very grateful to my collaborators here. And so let me introduce you to the Paul-Drude-Institut quickly, in case you've never been there, you don't know where it is. So it's in the middle of the city center in Berlin. So if you have a look here, and there's a small map, well, Paul-Drude would be around here, where I'm showing here with the laser pointer is this building at the Haus-Vogteiplatz, so a nice square that we have in the city center. So it's named after the German physicist Paul-Drude. And so the institute was founded in '92, and it originated from the Academy of Science, from the GDR. And so Paul-Drude consists of 4 departments, from epitaxy, spectroscopy, microstructure, technology, and transfer. So we are all under the director that is also professor at the Humboldt University. And all these departments, they work together at different core research areas. And I myself work on the epitaxy department, and I'm working on the core research area nanofabrication. But as I said, so we are collaborating so with other core research areas and so on, so that the knowledge is spread inside the institute. And so PDI has a staff of about 100 people, and from this 100, about 25 are permanent senior scientists. We usually have about 10 to 15 postdocs working there, and with about 20 to 25 PhD students. These are the usual numbers, and the rest of the staff is composed of administration and also technical staff. So it's a very nice place to be, because, well, besides research work, you can also do some nice sightseeing there. So if a postdoc working there says, okay, the research was not productive, at least he can say, I had a nice time in Berlin visiting museums and all the sightseeing places there. Yeah, so the epitaxy department is mostly dealing with molecular beam epitaxy, so MBE. For those who don't know, so MBE is a system where you basically grow your samples, usually under ultra-high vacuum regime. And so this is a picture here of a typical MBE system at the PDI. And so you basically have your so-called growth chamber, which is under UHV, usually 10 to minus 10, 10 to minus 11 millibar pressures. And so I don't know if you can see that here, but then you have basically some ports in this case here. So this is a system where the fusion cells, where basically you load the elemental material that you want to evaporate, they are loaded here. And usually in this case, the sample will be around here. This is an illustration here of a typical system, for instance, for use for growth of boron nitride, where we have the growth chamber, where we basically put our sample inside. We're able to rotate the sample and so on during growth, also for doing some spectroscopy and so on. And so basically you have then the different ports, as I mentioned, where you have the material that you want to deposit. In the case of boron nitride, basically we use a boron source that is loaded with an elemental boron, highly pure boron. Basically, we heat up this material to high temperatures, and then you get sublimation. And this beam of the material that you want to deposit is just hitting the sample, right? And well, we can also use plasma sources. In the case of boron nitride, we have the nitrogen gas going through the source, and then basically you generate a plasma, and this would be then the source of nitrogen. And of course, you have other ports where you can, for instance, monitor temperature through a optical pyrometer and so on. And in addition to that, you usually have some other chambers that are used first to load your sample inside the system, and in between the so-called load lock chamber, you usually have a middle chamber that, of course, prevents that your growth chamber will be vented every time that you load the sample. So ideally, your growth chamber always stay in vacuum. And in the middle chamber is also a place where you usually will then perform sample treatments like annealing before growth, because you want to really clean the surface of your substrate. You want to remove water or any other sort of contaminant. You may also perform other types of treatments like sputtering and well, different things that you can do at the middle chamber, so that when you move your sample to the growth chamber, so basically the surface of the substrate you want to grow is ready for the epitaxial growth. And well, at the PDI, then there are many different materials being investigated. So we have in total nowadays 11 MBE systems, and it goes from 3-5 nanowires being grown on different substrates to topological insulator, phase change materials. Here's an example of germanium antimony telluride, the topological, the phase change material being grown directly on silicon. Also more complicated structures like combining ferromagnetic materials with semiconductors. Here's just an example of cobalt iron silicide grown epitaxially on silicon substrate, and also 2D materials. That is an activity that we started there in 2010. And we've been dealing with different types of systems, not only growing a 2D material like graphene on substrates like nickel. Here I show you an STM image of graphene monolayer on nickel, where you can see this nice moire pattern coming from graphene. But we also have been preparing hybrid structures with very sharp interfaces. Here I give you an example of gallium nitride nanowires that have been grown on MLG. Here means multi-layer graphene, and you can see again the clear interfaces that are possible when you grow at very precise conditions and clean conditions like in MBE. And also van der Waals heterostructures. What does this mean? So you want to grow a 2D material on top of another one, and we will discuss more about that soon. And this is just an example here of HBN that has been grown on BLG, that here stands for bilayer graphene. Anyway, so there's a big zoo of different materials that we have been growing by MBE. And I mean, the main thing with MBE, as I already mentioned, is that you can grow at UHV conditions, ultra high vacuum, and this allows you to have very clean and very sharp interfaces. So MBE is a very a powerful tool if you want to start with a new material, and if you want to really try to get the best out of a material of a heterostructures, where you can really guarantee a very clean environment. And also the fact that you have UHV, you have proper conditions for in situ analysis, right? Like I mentioned, you could do some spectroscopy while growing, or yeah, as I will show, some electron diffraction, so-called read. So this is always very good to have, so you in order to perform fundamental growth studies. So with this, I come to the outline of the talk, and today I will show you two examples that we've been investigating at the PDI. First one is epitaxial growth of graphene hexagonal boron nitride heterostructures, van der Waals heterostructures. And a second example is a growth of ferromagnetic van der Waals heterostructures. So I will start with the first one here. And of course, the main motivation of this work is, as I already said, to prepare this kind of systems epitaxially. And why is that? I mean, you may know that since graphene has been first isolated by Andrew Geim and Kostya Novoselov, and they got the Nobel Prize due to their nice work on graphene. Of course, the field of 2D materials then expanded to many, many other material systems. And here is just an example of a graphic that shows some of the systems that have been explored. And for instance, their energy band gaps and so on, going from graphene, black phosphorus, all sort of 2D semiconductors, up to boron nitride here that has a high band gap. So it's an insulator material. And interestingly, boron nitride has exactly the same honeycomb structure as graphene. But of course, instead of carbon atoms, you have boron and nitrogen atoms that are periodically spaced and so on. So they have they are isomorphic to each other, and but with very different properties, going from graphene, a semi-metal, to a highly insulating material, boron nitride. And what's being proposed, what's being investigated, is that by many groups, is that you start now combining these 2D materials as vertical heterostructures, also as lateral ones, but today we're going to focus on vertical heterostructures. You can actually start building artificial 2D crystals that are hybrid 2D crystals that will show new properties and new functionalities that you will not see on the single 2D material. So this is very interesting because it opens the perspective to build up, to create atomically thin device structures that can be used for ultra compact applications and new types of devices and so on. And of course, the field is very fruitful, and there are many groups working on different types of devices and applications, right, from fundaments to applications. And I want to call your attention here to a very interesting material, that is the boron nitride. So in short, HBN. And I write it here that it's a key building block material for the heterostructures. And one of the most common use of HBN when it comes to these van der Waals heterostructures is it's used as a substrate. What it's been shown that when people start to exfoliate graphene flakes from this graphite crystals is that when you deposit that directly on silicon dioxide, you still get very high mobilities in graphene and so on. But you have a strong fluctuation in the surface potential in graphene, as you can see here. I think, if I'm not mistaken, this is a Kelvin force probe microscope image. And this is an STM image which shows how the graphene actually looks like when you deposit it on a typical silicon dioxide substrate. And then what was realized is that actually if you start depositing these graphene flakes directly on HBN, which is quite smooth, has 2D surface, you get very nice, this surface potential. It's much smoother than before, and this reflects on the mobility of graphene on HBN that is much higher than what you get on silicon dioxide. And well, you can see here by STM that the quality of the surfaces improves quite a lot. It's much smoother and so on. So this is I would say that the main use of HBN in this type of heterostructures. But in addition to that, HBN has been used as an encapsulation layer for some other materials like molybdisulfide or molybdiselenide. So 2D semiconductors, they are quite, they react quite quickly to under air exposure. So you want to protect them from the environment. And one of the things that you can do, you can encapsulate these materials with HBN. So it protects, let's say, from the environment, but also improves, for instance, the optical properties significantly. There are some work showing that. And in addition, so HBN has been used as a dielectric layer, as a tunneling barrier for more sophisticated structures, combining graphene with HBN, for instance, tunneling transistors, where what is nice to see that you can actually change the tunneling in HBN logarithmic when you start changing the number of layers. If you go from one monolayer to 4 layers, you can see this strong modulation in tunneling current and so on. Of course, again, this opens many perspectives in terms of device where by simply changing one atomic layer in HBN, you can see different effects. So, and what is the state of the art in terms of synthesis? As I mentioned already, so most of the time, people will take flakes from a crystal, from a bulk crystal, and transfer to a substrate, and they would do sequential transfers so that they can build up their structures. And it can also be layer transfer, meaning you grow HBN or graphene by a technique like chemical vapor deposition on a large area, and then you have to remove this layer from the host substrate and then start doing this piling up of different 2D materials. This is quite nice. This allows you to have many combination possibilities. You can play around a lot for basic investigation. It's quite nice, quite interesting. And so it's very good for device demonstration, but you also have many problems. And one of the problems is, of course, is not scale. So I show you here many examples where basically you see micrometer sized flakes and structures that have been produced. And in addition, what's being observed, that's usually, even if you do that quite well on a glove box and so on, you may end up with some contamination at the interface. Like this is an example where you basically have a kind of hydrocarbon bubble here, if I might use this word, which of course will kill any sort of a effect that you want to see at the interface and so on. This will be deleterious for any sort of device that you want to build up. And in addition to that, it's not scalable. So you cannot have a wafer scale showing reproducibility in terms of area, of course. So this is quite problematic. Here is just another example. You have HBN combined with moly disulfide, where you can also see this kind of contamination that's kind of trapped at the interface. And here another example where you combine like a single layer graphene with TMD and boron nitride. So very sophisticated structure, but it's a small area, and you may suffer from contamination. And again, you may even process this into a device like shown here with contacts, but at the end of the day, you have one single device. You don't have like millions of devices as you want to have in any sort of technological application integration. So ideally, what you want to do, you want to do a wafer scale van der Waals epitaxy, meaning you want to start growing, choose a substrate, you want to grow a 2D material, and then you want to come with another precursor and grow another one on top, and so on and so forth. So this, and you want to do that on a wafer scale, as I said. So in principle, beautiful, everything works fine. So it's a scalable, it can be arbitrarily large, and it's a transfer-free processing. You would have clean and sharp interfaces and so on and so forth. But of course, it's never like that. So you have many issues here. I will point out two issues here. The first one is thermal stability. If you're growing a material on top of each other, of course, you have to take into account growth temperatures. What do you need in order to get high crystalline quality and so on? And one example here, if I want to grow HBN on top of a metal dichalcogenide like moly diselenide, no chance this will not work, because for the temperatures I need for HBN, I will probably destroy the moly diselenide, or it will get very defective because selenium will evaporate and so on. So there are these issues in terms of compatibility, what you can do. And a second thing is that in van der Waals epitaxy, you would expect that ideally you have only van der Waals bonds between 2D materials. And the product of that, the direct product of that, is that when you start depositing by, for instance, MBE, the materials, the atoms that you need to grow your 2D material on top, they will immediately desorb, or they will have a very high desorption rate. That means growth will not be as effective as in the case of a conventional epitaxy, where you grow, for instance, a three-dimensional material on top of another three-dimensional one, where you have chemical bonds, strong bonding at the interface that favors the growth and so on. So there are many issues. This high desorption rate is one of them. And the question is, how do you get nucleation working during van der Waals epitaxy? Or how does it work at all? So there are many questions that have to be answered before one can really say we develop methods for van der Waals epitaxy, wafer scale. So, and this brings to the goal of the work here. So we wanted to look at scalable fabrication of this kind of 2D heterostructures using MBE, and we want to understand what's happening, right? So nucleation and growth behavior. And we use the example of HBN on graphene to start with our investigations. And so I go now to the part where I explain you what type of samples we have been studying. We needed to have, or we wanted to have a large-scale template for starting. And in our opinion, the best template you can get, it's epitaxial graphene on silicon carbide, because It's wafer scale and it's single crystalline, so it's ideal for this type of investigations instead of using, for instance, graphene that is grown by chemical vapor deposition and on copper, and then it's transferred to another substrate, because there you have a transferred material with a lot of contamination, so you don't really get a nice van der Waals surface. So we've chosen the epitaxial graphene silicon carbide. Very briefly, how this is grown. So you get a silicon carbide piece. In our case, we have a furnace for that. So it's a 1x1 silicon carbide piece. We load that in a furnace. We first prepare the sample with an etching, hydrogen etching at these conditions here. After that, we go for the graphene growth, which basically consists of going to very high temperatures, 1,600 degrees Celsius in an argon atmosphere. And what happens in this case is that silicon sublimates, silicon leaves the surface. And in a few words, what is left behind is graphene. So carbon is left behind. It reconstructs and forms a very nice epitaxially aligned graphene layer. Is that pure single layer graphene? So it's not. What we see here in the AFM is that usually what happens, so you have atomically flat terraces, which are here, you can see here, and in between these flat terraces, we have a step edge. This is coming from the silicon carbide, so it's represented here like this in this image here, where I have the silicon carbide in blue. So basically, you have an atomically flat terrace, you have a step facet, and the next terrace comes here. What we usually see, since nucleation starts in this epitaxial graphene nucleation starts at the step edges, you usually end up with some bilayer graphene or few layers graphene close to step edges, while the terraces are covered in single layer graphene. And in addition to that, we always have making the interface between silicon carbide and the graphene layers, which are decoupled from the substrate. We have the so-called buffer layer, which you can think of that as being like a graphene layer, which is partially bonded to the silicon carbide substrate. So you have some sp3 hybridization. There's not purely sp2, but you also have about 30%. This has been demonstrated by other groups that 30% of the bonding is sp3. That means it's bonded to the substrate. But nevertheless, the surface, it's a epitaxially aligned graphene surface that you get, so that is perfect for van der Waals epitaxy studies. And we have studied this type of substrate now for many years, and you can use Raman spectroscopy, for instance, to get information about the number of layers that you have close to step edges, like bilayer graphene and so on. While on the terraces you have single layer graphene, and this can be seen, for instance, by Raman mapping, where basically on the full width half maximum of your 2D peak, that is kind of a fingerprint for graphene, you can then get information about what kind of graphene you have there. So then we go for HBN growth by using MB. And essentially, as I already explained, we have sources for boron and nitrogen. These are the conditions I use here. I don't go in detail, but you can find that in some of our publications. But we vary growth temperatures. Basically, you are turning the knobs there in order to improve your growth, or in order to get some systematics, understand what's happening. So we first characterize, like we take the samples out and we characterize by Raman spectroscopy. And it's not so easy in this case to observe HBN formation. One of the reasons is that we do have a peak here, exactly where HBN signal should appear in Raman. That kind of overlaps to that. So this is due to the D peak that we have in graphene. So we do have some defects always, and it appears here. And on top of that, we know we did that on a previous study. We've seen that the buffer layer itself has a Raman signal that consists of a kind of a very broad band exactly around this area. That's why I write here D plus BL, that is for buffer layer. But if we move to excitation with ultraviolet laser wavelength, and then actually what happens is that this D peak and the buffer layer, they are strongly signal, they are strongly quenched, and well, because the D peak is actually energy dispersive, and so it shifts in energy and also decreases in intensity. And the good news is that then you are going close to the cross section in HBN because of the high band gap, so you are able to excite HBN. But it's a very thin layer that we are forming, and that's why you see a very small contribution of HBN. At least we know this is an indication by Raman that we form HBN. We move on in the characterization of other techniques like XPS, X-ray photoelectrospectroscopy. And what you do there, you go to the boron and nitrogen 1s core levels, and in order to see if you get a boron nitrogen signal, and we do get, and according to the binding energies, we can infer that we are forming the hexagonal phase and not like cubic boron nitride. But still, of course, this is not the ultimate proof. And in addition to that, we did a lot of TM investigations where we can see that we have HBN layers that are, of course, defective, as you can see here, but they are forming on top of single layer graphene in this case, or bilayer graphene. And you can see that although the HBN is not perfect, and I'll show you soon why this is the case, we do see a sharp interface forming between the two materials. But what I find nice, and I want to show you here, is how the nucleation takes place. So here I show you growth experiments for different times. Basically, we are keeping the flux of boron and nitrogen constant during growth. We are also keeping the temperature of the substrate of the graphene surface the same, in this case 850 degrees Celsius. And then we start growing first for 60 minutes, and we see almost nothing at the surface. It's still like pure graphene. We just see some islands that seem to be forming close to surface irregularities, let me say, like step edges or wrinkles that we have at the surface. Wrinkles is like they form in graphene, for instance, when you cool down graphene, the sample, the silicon carbide sample, when you cool down quite fast, what happens is that due to thermal expansion of graphene and silicon carbide being quite different, you end up having this deformation of wrinkles at the surface. And that's where we see that some material is nucleating, which we assume to be boron nitride. So you can see these tiny islands here. If you have a look here in this image, AFM, you also see very tiny islands forming where the height of these islands would correspond to a monolayer, a atomic layer of hexagonal boron nitride, about 0.35 nanometers. And only when we grow for a much longer time, which is pretty long here, and this is because we use a very low boron flux and nitrogen flux in this case. So it's expected you get this very low growth. On top of that, you have very high desorption of material, as I said before, because it's van der Waals epitaxy. You have a van der Waals surface, so most of the material, the boron and nitrogen that goes to the surface, it desorbs. But anyway, what you see here with time is that these islands laterally grow, and the height of these islands corresponds to, as I said, a monolayer of HBN. And what is interesting is that, again, that you see that this nucleation, the seeding is happening around defects. As I said, wrinkles or step edges. And sometimes you see islands that are purely monolayer, where most of the time you already have what we say a kind of vertical growth taking place in the middle. You see another area here where you already have some islands that are kind of merging to each other, and while we have this vertical growth going on. Anyway, if we grow then for 600 minutes, then we see the whole surface is covered with this additional vertical growth going on. So it's far from ideal. I mean, when you grow in MBE, you would expect a nice layer by layer growth where your surface is perfectly smooth, atomically smooth afterwards. And this is not the case here. And we believe this has to do with the fact that this nucleation is so disordered and you have vertical growth competing with horizontal growth. And I want to dig a bit more on this nucleation here, because what we see, as I said, we see these morphological features and the nucleation taking place there. But even if you go to specific areas where apparently you have a pure island growing on top of a graphene terrace, when we do some conductive AFM, meaning we are probing tunneling at the surface by using a metallic AFM tip, and essentially the dark areas here corresponds to a material that is insulator, and this is boron nitride in this case, while on the exposed graphene surface we have a higher conduction. That's what we're seeing here, and you can see that where we have this HBN islands forming, we have lower conduction, while the other areas, the exposed graphene is brighter. Anyway, what I want to show you here, the most important thing is that even for this monolayer beautiful islands, it looks like in the middle of that we have leakage path that allows for conduction in the middle of what otherwise insulating HBN. And so we propose that even point defects in single layer graphene would be responsible for our nucleation. So we kind of coined this as as defect mediated nucleation during van der Waals epitaxy. In other words, we don't have an ideal scenario where, as I explained before, just van der Waals forces are dominating, but we probably have some strong bonding there, maybe covalent bonding that is happening, and it's leading to the nucleation. And the problem with that is that, first, this seems to be happening in a general manner. It's not only related to HBN on graphene, but there are other examples of literature. For instance, CVD growth, chemical vapor deposition of disulfide on graphene. People see very similar things where wrinkles in graphene will lead to nucleation. Or tungsten diselenide on pyrolytic graphite. Again, this kind of a island growth with out-of-plane growth taking place, so no layer by layer as you would wish. And the same example here, HBN on pyrolytic graphite, very similar effects. There's also a group showing that when you grow, then the TMDC on HBN, very similar things happen, and they have some calculations that support that you do have this defect-assisted van der Waals growth, if you will. So this seems to be a general effect. But of course, the problem with that here is that if this nucleation is so disordered, then you would expect that this will influence the growth. And that's what leads, for instance, what we observe, that when we grow for a long time, we do see that we grow HBN, a few layers, but we still have vertical growth going on. And these are things that we want to avoid. And the question is, can we play a bit about with defect engineering in graphene so that we can improve the situation in terms of nucleation, right? Can we create a method that would allow us actually to exert control of this process? And that's what we tried to do here. So we got this graphene substrate. Here I'm not representing the buffer layer, but it's so only the graphene. So we do then, we use a helium-ion microscope from colleagues from Festkörperelektronik Institute to write a pattern of what we call irradiation-induced defects in graphene with low energy, helium-focused ion beam. And finally, we take the sample, put in the MBE, and grow HBN. And so if we are somehow right that even point defects would lead to nucleation and so on, we should be able then to start growing where we have these defects. So let me just show you here what we did. So we have some pattern that is created by optical lithography with some markers, like which leads to this square here. And in the middle, we create an ensemble of defects with different distances and so on. And just checking the time here. Yeah, and right. And then we use, for these defects that we are creating, different amount of ions per irradiation-induced defect, what I call here IID. So we use either 10,000, 20,000, or 40,000 ions per IID. And this is what is here in this pattern. So the pattern is not important. I'm just showing that because then we do some Raman mapping around one of these squares here. And as you can see, well, it's difficult to see, the markers are here in the corner. And in the middle where we have this pattern of defects. And we do see the trend that by looking in the Raman results, we do see this trend that the D peak, the intensity of the D peak that is related to defects increasing. And this should be like that because we are putting defects, and you see in the mapping here that the D peak intensity is increasing around this area as we expect. So good news, this helium focused ion beam can generate defects. And then the next thing is, okay, what happens when you grow HBN? And then that's what we got. Then here I show you this AFM image where we have these markers in the corner and in the middle. I don't know if you can see here, but here you can slightly see the pattern that we have. But this is easily seen when we do conductive AFM. As I said, you come with a metallic tip, and then you probe the surface, and you get information about the electrical properties, if you will. And what we can see here is that for the case where we have these defects created with 20,000 ions, helium ions per defect, we do see that we have these black dots in a pattern shape, as you would expect, because that's where we wrote our defects. And this is the case where we have 250 nanometers of spacing between the defects, and this is the case where we have 500 nanometers, where, as expected, and you see a larger separation between these tiny black dots, which, according to the conductive AFM, correspond to areas where we have insulating material, much lower currents. And if we look closer, we indeed see that we were able to nucleate these islands where we wrote the defect. We still see some parasitic growth happening, as expected, as I showed you before. But the bottom line is that indeed you have preferential nucleation around defects. And what is actually nice to see is that if you use 40,000 ions per defect, where we probably, I mean, we're still looking into that, but probably we kind of dig a hole in graphene. We have a non-hole there. It's not like a single vacance. And that's when we grow HBN, but it's more disordered, and we still have this out-of-plane growth going on. While if we use a lower dose, where we expect that the smaller defects being formed, but again, we still don't know what defect it is, but we do see an influence in the growth. By growing HBN with the very same conditions, we do have a preferential monolayer formation, so this vertical growth in the center decreased quite a lot. And what is nice to see is that if you look in detail, you see that most of the islands, they are epitaxially aligned, but the arrows here are kind of indicating the direction of the facets that you have on these monolayer HBN islands. And what is nice is that now if you look to the islands here by using the conductive AFM, you actually see some moire patterns happening in most of the islands. I mean, remember, this was done with normal AFM in atmosphere, so it's not a fancy AFM in UHV and so on, but still we were able to see this moire pattern. And if we now consider this island here and we have a look on the periodicity of this moire pattern, this corresponds to the most stable epitaxial alignment between graphene and HBN that would be 0 degrees, and as calculated shown in this paper, and this gives you a moire periodicity of about 14 nanometers. But so the takeaway message here is that this confirms that this defect-mediated van der Waals epitaxy is taking place, and that you can use defect engineering on your 2D template to modulate this epitaxial growth. Just going on here, now if we grow for a longer time, in order to grow a coalesced HBN layer, this is for the case in between 20,000 ions per IID. Not ideal, but that's what we had at the time. So the arrows here, they represent the metrics of defects that we are forming. And then we grow for a longer time, and then we see that we have merging of the islands until we form a closed layer of HBN. Not ideally a monolayer, but it's at least much better than what I showed you before, the 600 minutes, where we have a lot of out-of-plane growth. What is nice to see here is that you can get areas where there's twisting between HBN and graphene, where this is the case with this moire pattern of 14 nanometers, and there is this merging or this coalescence, lateral coalescence with HBN that is actually 5 degrees rotated to graphene, and this information you can get by looking into the moire pattern that is generated there. Just finally comparing electrical properties here. So we estimated that by using conductive AFM for a different number of layers, and we get results that are very similar to exfoliated HBN, not on top of graphene, I guess, but it's directly transferred to SiO2 substrate. But this shows that at least the grown material does not, it's not worse. It does not lose in quality in comparison to state-of-the-art flakes. So let me summarize this first part here. I'm not sure how I'm doing time, but I think I still have something like 10 to 15 minutes left. Is that the case, George? Or
yeah, that's right. That's right.
Okay, thank you. So this is the first part, epitaxial growth of HBN graphene heterostructures. I've shown you that you have this defect-mediated van der Waals growth. And if you have that, one way that you can actually benefit of these defects is that you use defect engineering on your substrate to try to improve growth, to attain control over nucleation, number of layers, during van der Waals epitaxy. And we believe that this kind of route is actually interesting for bottom-up manufacturing growth of other types of 2D heterostructures, and we've been trying recently to apply that for other materials. Now let me go a bit quicker than planned to the ferromagnetic heterostructures. I just want to say that if you look until a few years ago on this library of 2D crystals, as I showed you in the beginning, you would see the graphene and the 2D semiconductors, boron, nitride, but there is essentially no 2D magnet. And this was not seen as a big surprise because, well, what is expected according to the Mermin-Wagner theorem is that thermal fluctuations would actually lead to the absence of ferromagnetism or magnetic order long range in 2D systems. So basically the Heisenberg model here that you don't have spin alignment and so on. But what people observed in, I think, 2017, the first paper came, that for chromium iodine, flakes exfoliated from bulk crystals, as well as then 1 year later for iron germanium telluride, is that even monolayer thick flakes would show magnetic order if you perform, for instance, Kerr rotation measurements, so-called MOCA measurements, and they see this ferromagnetic order, which is believed to be related to a fact that these flakes have a very strong perpendicular magnetic anisotropy. That means the spins are aligned out of plane, and this probably is what allows for the stabilization of this two-dimensional magnetic order. And of course, what people always see is, as always in these atomically thin materials, if you have a magnetism that survives down to a monolayer, that is immediately then it's something that is very interesting for the design of new generation of spintronic devices that are atomically thin and so on. So a lot of interest merged in this new type of 2D ferromagnetic materials. And now you already have in 2022 a review putting here, for instance, a experimentally validated results for all different kind of 2D magnets. And I just want to call your attention here for this metallic system iron germanium telluride, which I say the FGT family, because if you look here, they have a very high transition temperature, always around 300 Kelvin, and they also have highly tunable properties. For instance, if you change the iron concentration, in principle, you can still keep the van der Waals structure, meaning layered material that would allow you to go to a pure monolayer and having a very high TC that will actually increase with the amount of iron because you increase the number of nearest iron neighbors. Of course, this is important to be able to have a Curie temperature around 300 Kelvin or even higher than that, because if you want to produce a device, you want to have that working at room temperature ideally, and not only at low temperatures. Anyway, I will skip this part here, but it essentially shows that it's theoretically predicted that these different phases are indeed stable in the 2D and the van der Waals phase. And in terms of synthesis, again, similar to the case of other 2D materials, it's still the state of the art. Are bulk crystals that are very tiny, and when you exfoliate flakes out of that, they are also micrometer size, not bigger than that. So again, same story. Development of large-scale epitaxy is highly it's mandatory. And of course, combining that with other 2D materials would allow to create another turning knob for controlling magnetism, while you have then this interface between different 2D materials where you could have different type of effects that would allow you to modulate magnetism. And so again, here our goal was to go for large-scale epitaxy, understanding large-scale epitaxy of this type of materials. We go to another MBE system there where we have sources for that, and we try to grow this iron germanium telluride on top of graphene, again using graphene, epitaxial graphene as a nice substrate for van der Waals epitaxy studies. So I go very quickly here, but the bottom line is that we have read investigation done in situ reflection, high energy electron diffraction, as well as grazing incident XRD diffraction that shows us that we've been able to grow this iron germanium telluride on graphene and epitaxially grown. We do have some mosaicity in plane. That means not all the islands that are formed and they coalesce, they are epitaxially aligned in plane. We have some mosaicity, But in general, in terms of van der Waals epitaxy, we have a very good quality. Interestingly, though, is that you see that FGT is actually epitaxially aligned to the silicon carbide below, parallel to the silicon carbide. So quite quickly here, we investigate transport in these materials, and we could obtain results that are the same as this state-of-the-art flakes. So basically, we have the anomalous Hall effect here, and when we do this transport, actually the resistivity is a sum of the ordinary Hall effect, that is basically a straight line, and when we have this hysteretic part here that is due to the anomalous Hall effect taking place in the ferromagnetic metal. And based on information from this here, we are able then to plot, for instance, the magnetic reproducibility fields that we have for different temperatures, as well as the anomalous Hall resistivity. And we can plot that as a function of temperature. And when these two properties go to zero at certain temperature, that is the temperature that you can take as the approximate Curie temperature, which in this case is around 220 Kelvin. And in addition, a very important information here, if we go to very high magnetic fields, we start seeing Shubnikov-de-Haas oscillations. This is not coming from FGT, but from the graphene below. And this is a very important thing because it shows that even after growth, the graphene layer below is still functional and is still showing very high mobilities. That's the reason you see Shubnikov-de-Haas oscillations, meaning you still have the manifestation of the quantum Hall effect in graphene, which shows that you have a heterostructure. So both 2D materials are still functional, which is very important in the context that you want to have both materials functioning there. Very quickly here about the growth properties. Again, is everything working finally here? That's not the case. What we see here, if we grow for 1 hour, we get a 10 nanometer thick iron germanium telluride film on graphene, but AFM shows that we have some holes in the film, like here. And this is exactly where we form this bilayer or few layer thick graphene, right? Meaning that even if you change one layer of graphene on your substrate, this influences the growth directly, where I need a much longer time to grow on the bilayer graphene areas in comparison to the monolayer areas. So, which is the light blue areas here is where FGT is covering, right? And one test that we did was the following. We took a sample of silicon carbide that has an off axis. That means we have a miscut in the wafer. This leads to a much higher density of step edges at the surface. And the consequence of having more step edges is that you are able to grow, to nucleate graphene layers more easily than on the other case. And this leads to a coverage, a surface coverage that is not monolayer graphene, but is completely few layers graphene. So that means we have 3 to 4 layers of graphene instead of monolayer on the terraces. And what we see that for the same growth time, the growth is much, much slower. And we get some thickness of about 4 to 5 nanometers, and it's not a continuous film. And why do I show that? Because now we come to the point, what is the kind of growth mechanism happening here? And again, I show that because that's what we are interested at in understanding what's happening here. In this case, we're not still completely clear, but it's interesting though that it seems that we are having 2 effects there. The first one, or the first, let's say, contributions could be coming actually from the substrate. What I mean by that is that the silicon carbide might be influenced growth in a method that in an effect that is called remote epitaxy. So silicon carbide is actually driving the epitaxial alignment of FGT, and it's also allowing for a much higher adsorption rate at the surface from the atoms. So it's a much more reactive surface. That's what you are able to grow a thicker FGT. Another thing that we know, this epitaxial graphene has a periodic corrugation that is created by the buffer layer underneath. It's not represented here, but on a large area, we have a surface that looks like that, where this kind of ondulation is promoted by the buffer layer. Thicker you grow your graphene, more far away you get from both buffer layer and silicon carbide. And so you go closer and closer to a case of ideal van der Waals epitaxy, where then the growth will have the other problems that we see in the boron nitride, like that you start having more vertical growth instead of lateral growth and inhomogeneous nucleation. That's what you see here, where you see this FGT islands that are growing close to step edges and so on, very similar to the case we observe for HBN and graphene. So if I mean, this brings me to the point here that a lot of innovative ideas in van der Waals epitaxy is needed nowadays in order to improve this growth of this type of materials. And I think this shows that it's quite difficult, because depending what you do, what you have at the surface, even again, if you change 1-2 graphene layers, you change the growth mechanism completely. So finally, another 2 minutes, and then I show you here, we want to increase this Curie temperature even more. For this FGT ferromagnetic material. And as I told you in the beginning, one of the ways of doing that is stuffing more iron within these layers. And that's what we did. We grew this iron 5 germanium telluride, and we get by XRD the information that we are growing the right layered phase with more iron stuffed in between. And that's what we get here, some TM, which proves that we do have a layered film of FGT that is growing on top of silicon carbide. Of course, it's not all perfect here. You can see here in this image that although we have the layered structure, especially close to the interface, we have some rotational disorder. They're within a very small area. You see different alignment of the FGT here. We also see that you have some van der Waals gap that finish in the middle of a layer, and you know, some stacking faults in general. That still show there is a lot of improvement in terms of crystal quality here. But the nice thing is that you look at this, another dark field example here is that you can see the graphene layers, and they are immediately followed by the FGT, the ferromagnetic layers here on top. And you have a sharp interface between the 2D materials, and the film is relatively smooth. But again, you have these problems close to bilayer areas where you have a kind of non-uniform nucleation. The most important practical thing here is that we do see an increase on the Curie temperature. So it goes beyond room temperature. Even at 360 Kelvin, we still see the anomalous Hall effect, which is a proof that the material is still ferromagnetic. We confirm that, for instance, by doing squid measurements, so magnetometry. And again, we see that magnetization remains beyond room temperature. And you see, in this case, we prove that it has a perpendicular magnetic anisotropy. That means the spins are aligned out of plane preferentially. And this is done by squid, in that you apply a out of plane magnetic field, and then you probe the magnetization. So this is quite promising for new future applications of these 2D materials in spintronic devices, and it's large area, so it's a patternable form of material. So in that case, I can say that we could advance beyond the state of the art that is this, as I said, flakes exfoliated from bulk crystals. So with that, I summarized this part, and so that we could achieve this large area growth. Graphene is actually not degraded during growth, which is good news, because you still want to use graphene as a functional material there. And it's nice to see that you can modulate, for instance, the Curie temperature by manipulating the composition of the films. And with that, I just want to make a general summary that the development of high-quality epitaxial growth of van der Waals heterostructures combining these two different 2D materials, it's a crucial step towards realization of new type of devices. So thank you very much for your attention, and I'm very sorry for extrapolating the time in, I don't know, 5 to 10 minutes. Thank you.
Well, that was fine. Very nice seminar, very didactic, very nice results. So this talk is open to questions. Does anyone have a question? You can either open your microphone or raise your hand. There is a raise your hand button in the. I do have a couple of questions. I wrote here. Is there any synergy to be gained from trying to do numerical simulations of how the growth process happens? Is that possible, or is that a pipe dream? Because I understand that's very difficult to simulate, but is there any work in that direction, trying to do numerical simulation of the growth, the dynamics of the growth?
I mean, that is something that I would be very interested in having a partner collaborator that could try to simulate these things. We've never done that. We cannot do that. It's not our expertise. And well, I already tried to consult with some partners, but you know, I could never really get someone interested on that because, well, people say, well, it's certainly a great effort, and you know, you have to get someone really interested on that. But yes, I think it's a very important thing that should be done because one of the questions for us is like, what kind of defect you need in graphene, or let me say, if you consider a certain type of defect on the graphene that is formed by this helium ion focus ion beam, how does the nucleation takes place, right?
Okay.
So you need some simulation to see when you have boron and nitrogen add atoms at the surface, how does the nucleation take place? What is the, for instance, what would be the best type of defect on graphene that would lead to this nucleation? And I think I show you there is some work, theoretical work done, for instance, in here, if you allow me. Oh no, I thought that you may actually check that. Quite interesting. There is, I'm sorry for that. Yeah, this here, this paper on tungsten disselenated on HBN, where they calculated this kind of possible, what they call the glue tungsten there, that would allow for this bridge between the two 2D materials. So I think there's a lot of work to be done in this direction for sure, and some calculations, some numerical calculations would be quite helpful. Yeah.
Okay. So Raimundo has a question. Your microphone is closed. It's off. Okay.
Yes. Thank you. Thank you, Joao, for the nice talk. I wonder how many samples do you have for all? I mean, in every system, do you use the same sample for all the characterization, or the growth are very well reproducible?
Fortunately, the growth is quite reproducible.
So do you have many samples, and you use different samples for different characterization, right?
It depends. I mean, let me tell you. So how do we usually do? We have this the furnace where we grow graphene. We can grow up to 8 pieces of 1 by 1 square centimeter, right? So we usually then do the following. We get silicon carbide. How can you do that very reproducible? It's very important. So you have a silicon carbide wafer that you try to stick to it, at least for a growth study, because depending on the miscut of your silicon carbide wafer, you may get graphene that is a bit thicker with more bilayer, more monolayer. But once you have a wafer, you stick to that, you grow like 8 pieces, or you do several series, let me say 20 pieces of epitaxial graphene on silicon carbide. And they are very similar in terms of properties, and then you conduct the growth, systematic growth in MBE. Basically, then you can be quite relaxed in that respect, because of course you can use one sample for many type of characterization, but you could also say I grow 2-3 samples for different methods, and they are quite reproducible. That's the nice thing about MBE. Once your template is reproducible, in this case epitaxial graphene on silicon carbide, the parameters in the MBE are also very reproducible. That's the nice thing. That's why I mentioned in the beginning, if you start transferring graphene, for instance, you grow graphene on copper, transfer to SiO2, and I'm not an expert on that, but I know people working with that, and they honestly tell me that it's not so reproducible as in the case of silicon carbide epitaxial graphene. So, and in this case, we are quite lucky, because both MBE and the furnace for epitaxial graphene leads to very reproducible samples. Yes.
Okay. Thank you. May I have another question?
Sure.
Yeah, from my side, I have the whole night here.
About the last system, you told FGT, right?
Correct.
I saw so many stacking folds, features in the layer by layer formation. Are you interested in quantifying or working on the density of these defects and how they influence the magnetic or electric properties, or no at this moment?
Yeah, that's a very important question. Yes, we are very interested. As a matter of fact, something I did not mention here is that lack of time. If we look in this image here, like now dark field, let me put the laser again. It is quite interesting because what we see is that if I look at the thickness of these very first layers here, if I would calculating them, they are actually thicker than what you would expect for this iron 5 material, or in reality we know we have 4.7, but they are thicker than that, and this indicates that we are actually having some what I call stacking faults, meaning we have some layers that are thicker than iron 5. They're probably iron 6 or even iron 7 germanium telluride, which are expected to have even higher TC. And indeed we see this Curie temperature around like 390, 380 Kelvin, which is much higher than other groups have been reporting. And we believe that this is related to this kind of disorder that we have now that allows us to have this higher TC. And we are definitely very interested on that. We are looking into that nowadays. First, we want to understand what these stacking faults are doing, for instance, to magnetotransport and ferromagnetism. But in addition, we want to do this better, that we control that even better, because we want to say at the end of the day, we want to be able to get rid of this kind of stacking faults. Even if we lose in TC, we want to try to improve that. One of the ways I did not mention, we can perform annealings after growth, so that we should be able to go to a more ordered structure by simply, minimization of the energy in the system. Yeah, but that's a very good point. Yeah, thank you.
Great. Thank you. Again, congratulations.
Oh, thanks a lot.
Okay, any more questions? Either raise your hand or open your microphone and turn on your camera. I have a couple of questions. You mentioned samples of one square centimeter. That's
correct.
what you managed to grow. Whoa.
No, that's.
I thought they were tiny.
No, they are. You see, you're still seeing this slide, right?
Yeah.
Yeah. For instance, this when I say here 1 square centimeter, meaning
I see.
we grew this size, and we actually perform magnetotransport on these very large sizes. In principle, we also grew. I do not show here, but this FGT can also be grown on sapphire wafers, and then we grow 2-inch wafers, and they are very uniform. Of course, silicon carbide is very expensive, still very expensive. And that's why we get the wafers, we cut them in small pieces, 1 by 1, sometimes half by 1. But this, the growth basically depends on the size of your MB system. If your MB system would be for a 2-3-inch wafer, as some groups have, then in principle you could grow. It's just related to geometry of the system. Yeah, but they are very large, of course. In comparison to these flakes, this is a big leap, right?
Okay, yeah, I was surprised when you said that you did measurements on squid. I said, well, what is for the squid?
No, yeah.
I thought you need a big sample, and they are big, so that's why.
Well, for the squid, you actually need a teeny tiny sample, right? So it's about a few millimeters, 2 by 2 millimeters, but then we cut the sample. For squid, then we cut the sample. Yeah.
Yeah, but I thought it was way smaller than millimeter. That were small flakes that you were growing. Okay.
No, this is it's really thin film growth there. Yeah, that's what we want to go for. Yeah.
Okay, so Denike has a question. Please go ahead. You have to open your microphone.
Yeah, I'm fighting with it. Sorry.
Okay.
So,
okay, no problem.
Hello. So nice to hear a Brazilian from Germany as a German in Brazil.
Yeah.
So,
how are you?
Thank you. So just just as somebody that's in the field and I'm somebody that comes from a different era of 3.5 growth, of course, I have to like make a more nasty question. So
Right.
how do you think the overall development of the 2D material growth is like, especially if you compare CVD, MBE? I have the feeling that there is a lot of struggle. I mean, you basically showed this very nicely in your talk. There seems to be a lot of struggle towards high quality material, and it seems to be the thing that you need to basically really do something more than basic research with this kind of materials. So what's your opinion? Is how are our chances that we see this happening?
Yeah, that's a very nice question. I would say if I would be, I would give you a short question. I would say you have to be patient because it's like comparing maybe, I don't know exactly when people start growing gallium arsenide or 3.5 structures, right? So you now have like in gallium arsenide or 3.5 structure, they are highly perfect nowadays, right? So growing from quantum dots to quantum cascade lasers, it's amazing what you guys can grow. But you are talking about a development in terms of material growth. Not, if I'm not, correct me if I'm saying something wrong, but that starts probably, I don't know, in the 80s or even before that, right? The first MBE systems.
So first MBE systems was 74 in Bell Labs,
right.
but they grown the first laser less than 10 years later. So
Exactly. No, that's what I was going to say.
We doing 2D growth longer than this, but I mean it's really like it's really hard to.
That's what I was going to say next, is that like I'm afraid that now I don't know, maybe MBE growth or in general, I think you are now on these 2D materials in general, something like 15 to 16 years that people are investing on that. And I guess the progress, it's definitely much slower than what happened on the 3.5 business, for sure. And you've seen there, I mean, this van der Waals epitaxy is a wild horse thing. I guess what is well established nowadays, it's like growth on metal surfaces. So we worked also on that. I did not show today, but growing HBN on a nickel surface, on a copper surface, or graphene on these surfaces, I would not say is easy, but it works quite nicely, right? And even MBE, I would say, is not the method of choice. In that case, CVD is even better, but still it works quite nice because you have a very strong atom diffusion at the surface and so on. I think that the most complicated thing is really this van der Waals epitaxy. And now going on and say, honestly speaking, I guess it will not work for all sort of materials. Like I still don't see how one can grow boron nitride on top of TMDCs like selenides and tellurides, because they are simply not stable. You can grow some boron nitride, but it's low quality, maybe some polycrystalline material. So I'm skeptical that epitaxial growth will serve for all material systems. I believe that you could play a bit with what I presented today, selective area epitaxy, where basically you could grow over a wafer scale, but never really a thin film, but growing for maybe direction of very selective on specific areas of the device and so on. But it's very challenging. I like it because it's nice to work on this field that is challenged, but I'm skeptical that this would be like a universal thing, that in maybe another 15 years, maybe we talk again, and then you tell me, yeah, it's now you have maybe 5-6 material systems. I mean, what we see now for the tellurides, this is quite nice because it requires low temperature, and we can grow with high precision these things. This work, it seems to be a very forgiving material system, tellurides and selenides. But still, as long as we are on these low temperatures on graphene, on HBN, having to do like very sophisticated and complex structures with more or let me say growing graphene on top telluride would not be possible. So maybe one would have to consider, and hopefully the transfer methods will develop more and more, that one could maybe do hybrid systems like partially transfer and so on. Yeah. I think that's somehow there is a future ahead that is partially quite exciting, but partially is actually, sometimes you think I would go back to 3D materials and, Yeah, but it's a nice point. Thank you.
Yeah, thank you for the honest answer. No? Okay.
Okay, I have a further question. On your slide 31, well, you closed the presentation,
No,
but
I can go again.
Slide 31. You were 34, 32, 31. Is that, yeah, you mentioned that there is a large magnetic anisotropy, so in that case it would be an Ising model maybe that would describe better the as a model,
Yes.
the magnetic system, and then this could explain the high TC temperatures, right? Because the Ising model has higher TC temperatures than the Heisenberg model because of the less quantum fluctuations.
That's correct. That's correct. But I mean, I know from some works, right? We never try to really fit our, for instance, our squid curves. We never try to fit considering, for instance, Heisenberg model. And one of the reasons that in our case, as I was describing before to the other colleague, that we have this stacking faults, we have different phases. You can see that our squid curve does not really, it does not have this shape that really goes abruptly to zero, indicating a phase pure material, but we have many probably different phases there and so on. But I know from another group growing more phase pure iron 5, and they are also not able to fit to a perfect Ising model. I think things are more complicated in a perfect Ising model. Yeah, but in general, this perpendicular magnetic anisotropy is confirmed. For instance, here what I show is like they show this MoCA, right, measurement, so the Kerr rotation, and the magnetic field is actually out of plane. So you only see this hysteresis if you do have spins out of plane, right? And the same is the case here. But you're right. It should be Ising model, but it's not that easy. Yeah, and there are also some systems. I think chromium bromine, the group from Max Planck, Stuart Parkin, they have been able to grow a monolayer islands or on epitaxial graphene by MB, and they actually see, interestingly, for this material system at very low temperatures, the XY model seems to describe better the results they have, meaning in-plane magnetization. Yeah.
Okay, thank you. Let's see if are there any more questions. I am not sure. Hiroki had to leave because he's managing the conference. He's the organizer of the conference, but he was here until the end, but he's not here for the questions. I was going to ask him, do the FT can help with, like you said, the understanding the defects made by the radiation with it's helium, right? It's helium plus that you use.
Yeah, we use helium. We have a partner on the project on this material. I don't know if you know him. He's an expert on DFT of irradiated materials. It's Arkady Krashenikov, and so he's looking essentially on the formation of these defects by DFT. But what we are not that far now in understanding how nucleation takes place or how growth takes place. I think for this molecular dynamics would be quite
dynamics. Yeah, that's right. What I would think. Yeah, molecular dynamics.
Yeah. This would be very helpful. Yeah.
Okay. So thank you very much for your time and your very nice talk. Let me stop recording.